Hello guys, my name is IBM and today I've decided to take you through the concepts of capacitance. This is going to be lesson 1 of capacitance. Now the basics here, these are the basics which are just required for a student doing Cambridge A-level physics, that is 9702. These are basic concepts. We shall not go into the details of how actually a capacitor works. The details of how actually a capacitor works will be found at a higher level. So in this lesson, I just want to introduce the basics of capacitance. This is the third topic that I'm covering after covering astrophysics and cosmology. After covering nuclear physics, today I decided to start a series of capacitance. So this is going to be lesson 1. So without wasting time, let's drill into the basic key concepts that a student requires to know for paper 4, 9702. So to start with, we should understand the meaning of the word capacitance. So to understand the meaning of the word capacitance, or before we know what a capacitor is, let's first understand the meaning of the word capacitance, because the meaning of the word capacitance will help us to understand how really a capacitor works. But I said we shall not go into the deep details of how it really works. So to understand the meaning of the word capacitance, we shall first consider an isolated conductor which is connected on a high voltage supply as shown here. So if we consider a spherical conductor which has been connected to a high voltage supply, observations show that as the potential difference or as the potential V on the sphere is increased, the charge which is stored on the sphere also increases. So that means the variation of Q on the conductor with the potential V is supposed to be a straight line. So if this is a variable, if we have a variable power supply, let me put an arrow in it to mean that this is a variable power supply. So we adjust the potential, we adjust the potential here so that more charges accumulate on the sphere. From your concepts of electric fields or from the concepts of electric fields that we shall see in one of the videos, we shall see that when a spherical conductor or when a conductor is charged, actually charges reside just on the surface of the conductor. So uh, as we adjust the potential or as we change the voltage supply here, it means more charges accumulate on the sphere, which means the higher the value of V, the higher the value of the charge, or the higher the value of the total charge on the sphere, because more charges accumulate on the sphere. So that means if we were to sketch a graph of either V against Q or Q against V, then we would get, or we would essentially get a straight line as shown by this graph. So a graph of Q against V is going to be a straight line. So what can we note from that concept? What can we note from there? If a graph of V against Q is a straight line, then it means that Q is essentially directly proportional to V. So since the graph is a straight line, because as we increase the potential, more charges accumulate on the sphere. That means the higher the potential supplied to the conductor, the most charges stored on the conductor. So V and Q are directly proportional. So if we remove the proportionality sign from Q directly proportional to V, if we remove this proportionality sign and introduce a equal sign, then we must also introduce a constant, and that constant is going to be labeled C. So what does C stand for? So the constant C stands for the capacitance. C is a constant, and this is going to be determined by the size and shape of the conductors. In the previous case, the conductor was spherical. In some cases, the conductor would be cylindrical, or in some cases, the shape of the conductor would be just a planes, parallel plates, In some cases, the conductor could be very large or could be very small. So C is the capacitance, which is going to actually depend on the size of the conductor we are considering. Therefore, when we talk about the capacitance of a conductor, we are referring to the ratio of the charge on the conductor to the potential on the conductor. Because when I see the subject from this expression here, the constant C is going to be Q over V, and C is the capacitance. So it is the ratio of the charge on the conductor to the potential on the conductor. It is the ratio of the charge on the conductor to the potential on the conductor. That's what we mean by capacitance of a conductor. It's not the capacitance of a capacitor. I just said in general capacitance of a conductor. The ratio of the charge on the conductor to the potential on the conductor. That's what we mean by the capacitance of a conductor. Of course, the unit of the capacitance in memory of a scientist called Farad, the unit of capacitance is going to be the farad, which is going to be capital F. But we can define what a farad is. If farad is the unit for capacitance, and we know that capacitance is charge, which charge is measured in coulombs, divided by potential, which potential is measured in volts, it essentially tells us that 1 farad, which is the unit of capacitance, is the same as 1 coulomb per volt. So the examiner may ask you to define what is meant by capacitance. So the capacitance of a capacitor, the examiner may ask you to define what is meant by a farad as a unit of capacitance. So the farad will be simply defined as 1 coulomb per volt. That is the farad. We can always define units in terms of other units. So the farad can be defined as 1 coulomb per volt. One important thing we need to note is that the capacitance of real capacitors that we shall be talking about is usually expressed in microfarads, nanofarads, picofarads, because they are normally too small values. If you check in your laboratory, you may have found some of these capacitors in the laboratory, and they have been labeled mostly microfarads and maybe picofarads. I haven't seen nanofarads in my laboratory, but you'll find capacitors measured in, labeled microfarads and nanofarads or picofarads. So these are commonly smaller values. So expressing them with such prefixes is still very convenient, so that their values do not look clumsy. So the word capacitance is involving charge per unit potential. And we noticed that in the previous example, the charge was distributing itself all over the spherical conductor, so that the potential at every point of the conductor is the same. What does that mean? It means that we cannot use the word capacitance when we are referring to an insulator. We only refer to a conductor when we are using the word capacitance. Now the question is why? Why can't I say capacitance of an insulator? Or why can't I use the term capacitance when I'm referring to an insulator? When we talk about capacitance, the charge placed on the conductor must redistribute itself uniformly all over the conductor, so that at every point the potential is the same. That's how we can use the ratio charge per unit potential, or charge over potential, because the potential at every point of the conductor is going to be the same. So for an insulator, we know that insulators not allow free movement of charges. Insulators prevent or block the free movement of charge carriers. And for that reason, if we have an insulator X, if I have an insulator and I add a charge, or I connect a power supply to one end, let's say I have a power supply to this end, a variable power supply connected to this end, and this is an insulator. So it means because this insulator does not allow free movement of charge carriers, it means the potential this side is not the same as the potential the other side. Therefore, I can't use the term capacitance as being charge per unit potential, because charge does not distribute itself uniformly all over the insulator. The charges will accumulate around this point, and they will not be free to move to the other end. So the term capacitance, or the word capacitance, cannot be applied to an insulator. So I'm saying when a charge is placed on a conductor, the charge distributes itself on the conductor, so there is one value of potential for the whole conductor. But then, to define a capacitance, the whole conductor must have the same value of potential as I've just mentioned. But within an insulator, the charge would not be able to move. The charge, as I've said, would not be able to move, so that there would be different potentials at different points on the insulator. So how would you therefore define capacitance, yet the potentials at different points of the insulator are different? For that reason, therefore, I am saying the term capacitance does not apply to an insulator. The term capacitance will not apply to an insulator because the potentials at different points or at different sides or different ends of the insulator will be different. So there is no way you will use capacitance, the term capacitance, there's no way you will find a constant ratio of charge per unit potential or charge to potential, yet the potentials at different points are also different. So in a nutshell, I'm concluding by saying the term capacitance does not apply to an insulator. I want you to also note that circuit components which have capacitance, we shall call them capacitors. So I've been talking about capacitors, and I said you would see capacitors in your laboratory. Every science laboratory should have capacitors. And of course, you have seen the pictures on the front page, on the first on the first slide. So those components which have capacitance, we shall always be calling them capacitors. By the way, all objects, all bodies have some capacitance. Even yourself, you have some capacitance. That is why you may become charged up by rubbing against a synthetic fabric. If you rub your body against a synthetic fabric, your body may end up attracting, maybe a balloon can stick on your skin if you rub your skin against a synthetic fabric. So we also have some capacitance. We also have some capacitance. In that case, if you rub against a synthetic fabric, you will be at a high voltage and therefore you will store a significant amount of charge. And if you try to discharge yourself by touching an earth metal object, you would feel a small spark. It may not be dangerous, but you may feel a small spark. So that means each of us has some capacitance. So if you rub against a synthetic fabric, you are going to store a significant amount of charge. And I'm saying if you try to discharge yourself by touching an earthed metal object, you would produce a spark. The spark might be very, very small. I always experience those sparks every time in my house whenever I whenever I spend much time doing work and I touch metallic objects which are earthed, I always feel those small sparks. So because I have some capacitance. So for a spherical conductor like the one we have just considered, whose radiuses are maybe insulated from the surrounding as we have seen, and carrying a charge q, then the potential on its surface is given by this expression here that you must have seen in electric fields. So if I have a spherical conductor sitting on an insulator, that means the charges are not being lost to the surrounding, and it is connected to a power supply as we have seen. One is positive, one is negative. So it is now being charged to a charge q and is at a potential V. The radius of the spherical conductor is R. Um, by definition of electric potential, remember, as the work done in moving a unit positive charge from infinity to a given point, you must have obtained from your unit of electric fields that potential is given by kq over R, where k is given as 1 over 4 pi times epsilon naught. And in electric fields, in a unit called electric fields, epsilon naught is called the permittivity. the permittivity of free space. So epsilon naught is called the permittivity of free space, and it is given in the list of constants. I think it is always quoted as 8.85 times 10 to the power of minus 12. This is given in the list of constants as the permittivity. We shall, if you have not seen electric fields before, we shall explore this in more details in a unit called electric fields. So the potential on the surface, because this is spherical, the potential on the surface is given by Q over 4 pi epsilon naught times R, where Q is the charge on the sphere, epsilon naught is the permittivity of free space, and R is the radius of the sphere if the conductor is spherical. Then if I use the definition of capacitance as charge per unit potential difference, so capacitance equals to charge over potential. So this would be the charge divided by the potential, which potential is Q, divided by 4 pi epsilon naught times R, which is the same as Q over 1 times the reciprocal, which is going to be 4 pi epsilon naught times R divided by Q. So Q cancels out. And this means the capacitance of a spherical conductor is simply going to be 4 pi epsilon naught times R. So the capacitance of a spherical conductor is always going to be given by that expression there, which may be very important in calculations. The examiner will ask you to show that the capacitance of a spherical conductor is given by that expression. Okay, so let's see a few examples. Having known what the capacitance is. Most of these examples are very easy. They just require using a simple formula, and an A-level student might not require my input in doing this. By the way, do not forget to watch the solved past paper questions. They will be the best in teaching you how to deal with capacitance. So, examples, let's try to see number one. If the radius of a spherical conductor is R, what is the capacitance of the conductor? So I've just said by definition of a capacitance of a conductor, capacitance is charge per unit potential, and we have said potential V is equal to a constant K times Q over R, which is the same as Q divided by 4 pi epsilon naught times R. So it means the capacitance therefore is going to be equal to the charge divided by the potential, which is Q, divided by 4 pi epsilon naught times small letter r. So it means you get the reciprocal. So this will be Q times 4 pi epsilon naught r divided by Q, and Q cancels out. So it means the capacitance C is going to be equal to 4 pi epsilon naught times r. So that will be the capacitance of the spherical conductor. So the capacitance of a spherical conductor is just dependent on the radius of the sphere. Because remember, the charge of a conductor resides on the surface. So it means inside the conductor, the net charge is zero. That's why later on in electric fields, or you might have said in electric fields, that the potential, the electric field strength inside the conductor was zero. We shall see that under electric fields. So that is question number one. Question number two, calculate the charge stored on an isolated conductor of capacitance 470 microfarads when it is at a potential of 20 volts. Okay. So I think I'll use this space. I don't know whether the space is enough, but I will try to use this space. Let me use this space. So I want to find the charge. So because capacitance is Q over V, so it means Q, which is the charge, is going to be C times V. So I'll just multiply this. C is 470. Micro is 10 to the power of minus 6. Then times the potential, which is 20 volts. So I'll just press my calculator and verify if the answer is correct. So 470 exponent minus 6 times 20 So the capacitance is 0.0094. I mean the charge is 0.0094 coulombs. So that is the charge, which means this answer is correct. Question number 3. The charge on a certain isolated conductor is 2.5 times 10 to the power of minus 2 coulombs when its potential is 25 volts. Calculate the capacitance. So capacitance is equal to charge over V. If you're a teacher, encourage your students to always write a formula. I always find challenges when we are marking exams, when the marking scheme tells us not to give a credit a mark if there is no formula and the substitution is wrong. So if you're a teacher, encourage your students to write a formula so that even if they mess up the substitution, they still retain 1 mark for the formula. So capacitance is equal to Q over V, and the Q has been given as 2.5 times 10 to the power of minus 2 coulombs divided by V, which is 25 volts. So just press your calculator. 2.5 exponent minus 2 divide by 25. So this is 0.01. I mean 0.001. Of course, the units are farads. So that is the capacitance. Question number 4. Calculate the charge stored. By the way, later on we shall see that a capacitor does not actually store a charge because total charge on the capacitor will be 0. Calculate the charge stored by 220 microfarad capacitor charged up to 15 volts. So here I'll just write a simple formula. Charge is equal to C times V. When I substitute, C is 220 times 10 to the power of minus 6, then times V, which is 15. So from my calculator, 220 exponent minus 6 times 15. So this is 0.0033 coulombs. So I think this is correct, which is 3,300 micro coulombs. Of course, to change to micro, you divide by the prefix, which is, if I want it to be in micro, I will say 0.0033 divided by 10 to the power of minus 6. The answer will be in micro, and I think that is correct. Then example number 5. A capacitor stores 1.0 times 10 to the power of minus 3 coulombs of charge when charged to 500 volts. Calculate its capacitance in farads, microfarads, and picofarads. So capacitance is equal to charge over V. So the charge is 1 times 10 to the power of minus 3 divided by V, which is 500. Let's first press the calculator in farads. So in farads, it is 1 exponent minus 3 divided by 500. In farads, I'm getting 2.0 times 10 to the power of 6 farads. So in farads, it is correct. In microfarads, we divide by 10 to the power of minus 6. So capacitance is going to be 2.0 times 10 to the power of minus 6 divided by 10 to the power of minus 6. And I think this will be 2.0 microfarads, which is correct. In picofarads, pico is 10 to the power of minus 12. So in that case, capacitance is going to be 2.0 times 10 to the power of minus 6 divided by 10 to the power of minus 12. I'm saying pico is 10 to the power of minus 12. Whenever you want to bring a prefix, you divide by its value. Whenever you want to remove a prefix, you multiply by its value. So we are bringing the prefixes. Pico is 10 to the power of minus 12. So I'm dividing by the value of pico. So when I divide this, 2 exponent minus 6 by 12 power minus 2. So this is giving me 2.0 times 10 to the power of 6 picofarads. So that is, I think pico is small letter p. So this is picofarads. Okay, I think those are insightful examples. They are not really very hard. They are simple. They are simple examples. Example number 6. Calculate the average current required to charge a 50 microfarad capacitor to a PD of 10 volts in a time interval of 0.01 seconds. So we want to find the average current required to charge 50 microfarad capacitor. So we have the capacitance and we have the PD, and we want to find current. So I think I'll use this space above here. So current by definition is the ratio of, or it is Q times T. Sorry, not Q times T. I is Q over T. The rate of flow of charge carriers, so it is Q over T. Current is the rate of flow of charge carriers, so that will be Q divided by T. And remember that charge is equal to, charge is C times V, because C is Q over V, so charge is C over V. So this means, or this implies, that the current is simply going to be CV divided by T. So I'm going to just substitute in that equation. So current is equal to capacitance, which is 50 times 10 to the power of minus 6, then times V, which is 10, divided by T, which is 0.01. So I'll just press my calculator. So 50 exponent minus 6 times 10 divided by 0.01. So this is giving me 0.05 amperes. So the answer here is given in milliamperes. We can check this. If I want to bring milli, remember milli stands for 10 to the power of minus 3. So this would be 0.05 divided by 10 to the power of minus 3. So let me try to divide the answer by 10 to the power of minus 3. And this is giving me 50 milliamperes. So if the answer is required in milliamperes, I think that is correct. Then Canesa connects an uncharged capacitor of capacitance C in series. Canesa is a name, it is a random name, I think. With a resistor, a cell and a switch. She closes the switch and records the current I at time intervals of 10 seconds. So after every 10 seconds, the results are shown in the table below. The potential difference across the capacitor after 60 seconds was given as 8.5. So it means when it is fully charged, the potential across the capacitor is 8.5 volts. Plot a current time graph and use it to estimate the value of C. So we are plotting a current against time graph. And you can try to plot these values and see what you obtain. But I've tried to just plotted this. So if you try to plot a graph of I against T, of course you don't expect, many times in paper 4 you don't expect plotting. I've never seen a question of plotting. Of course sketching graphs is there, but plotting has not really been there. But if I plot a graph of current against time for these values which were given, this is the graph that I obtained. It is an exponential. It's kind of exponential. At t equals to 0, the current was 200. T equals to 10, the current is 142. Of course, the scale on the vertical that I used, you can plot the graph yourselves. The scale on the vertical I used is one small square representing 10. So I plotted 20 against 102. Approximately there, then 30, approximately 75, then 40, 51, then 50, 37, and so on and so forth. So this is just a scale. A scale. You can plot a better graph using a better scale if you want. So the question was plot a current time graph and use it to estimate the value of C, where C is the capacitance. Now you may ask yourselves, how will I find the capacitance from a graph of current against time? We noticed that current is equal to Q over T. Current is equal to Q over T. And Q is equal to I times T. So that means, and we know that I times T would be equivalent to the area under the graph. So it means the area under this graph here is going to be equal to the charge on the capacitor. So it means I will simply say that the charge Q, because Q is IT and it is equivalent to the area under the graph, so Q is going to be equal to the area under the graph. Q is going to be equal to the area under the graph, and you notice that you can even check if the units are going to be columns. Here you have seconds and you have ampere seconds. Of course, ampere seconds, that is the unit for charge. So it means Q is going to be the area under the graph. So it is going to be your task to find the area under this graph. There are several ways that you can use to find the area under the graph. You can divide it into several shapes and you find the area. I will not find the area, but I will give you a hint. Divide under several shapes. Maybe that is one shape, two, three, and maybe four. So you find the area of all these shapes. You can first find the area of the normal shapes, the regular shapes. And then, of course, in your mind, you should be knowing what the area of one small square is in terms of charge. So on the x-axis, one small square is equal to 1 second. On the vertical axis, one small square is equal to 10 microamperes. So 1 square is equal to 10 times 1, which is going to be microampere seconds. That is one small square. One small square is going to be 10 microampere seconds. So if you have the area, of the regular shapes, you just multiply it by what one square stands for. I mean, if you have the area of the regular shapes, you'll add the area of the smaller squares. The remaining squares, you'll count the full squares, and you multiply by 10 microampere seconds to get the area of the full squares. Then you get the area of the half squares. So Q will be equal to the area of the regular shapes you have got plus the area number of small squares times 10 microampere seconds. That is now the area of the full small squares plus the number of half squares times half of the area of one square, which will be 5 microampere seconds. You must have used this method in AS of finding the total area under a graph which is not a regular shape. You can first come up with the regular shapes and find their areas. By the way, you could also find just triangles. You could draw triangles in here. Let me see if I can draw triangles in here. You could draw a triangular shape, and find its area. Then you can draw another triangular shape here, or a trapezium, whatever shape you want, and find the area. What we are trying to look for is the area under this graph. So whatever method you use to find the area under the graph will give you an approximate value. So if I know the value of the area of one small square, if I first remove the full shapes, I count the full squares remaining outside the regular shapes. Then I multiply by the area of one small square. Then I count the half squares. These are squares which are not full. The squares where this line crosses, I count those half squares. So because they are half squares, then I multiply by the area of half a square, which is 5. Then I sum up to get the charge. So I carried out this on a graph paper, and I actually verified that the area was approximately, the charge was approximately 5.1 millicoulombs. And if the charge is approximately 5.1 millicoulombs, remember capacitance is equal to charge divided by V. So this was 5.1 millicoulombs, that is times 10 to the power of minus 3, divided by V. I think V was given as 8.5. So when I press my calculator, 5.1 exponent minus 3 divided by 8.5. So this gave me a 0.0006. 0.006. These are farads. This is not microcoulombs, it is microfarads. So if I change to micro, I divide this by 10 to the power of minus 6. Let me try to check. Divide by 10 to the power of minus 6. This gives me 600 microfarads. So if you use the formula for finding the area, you may not get exactly what I've obtained here. You may not get exactly 5.1. You may get a slightly different value, but it will be very close to this. That's why I wrote here approximately. You just need the area under that graph, and that will be the charge. And then using capacitance is Q over V, you will be able to find the capacitance as approximately or very close to 600 microfarads. Okay. Then lastly for this lesson, estimate the capacitance of the Earth given that it has a radius of 6.4 times 10 to the power of 6 meters. So assumption, we can assume that the Earth is spherical. So if the Earth is spherical, then it means the potential on the surface of the Earth is going to be given by the charge on the surface of the Earth divided by 4 pi epsilon naught times the radius of the Earth. And we know that the capacitance is Q divided by the potential, which we saw that this would be Q times 4 pi epsilon naught R divided by Q, where Q cancels. So the capacitance on the Earth is going to be simply 4 pi epsilon naught times R. When I make substitution, this will be 4 pi Epsilon is permittivity of free space, which is 8.85 times 10 to the power of minus 12. This is always given in the list of constants. Then times R, which is 6.4 times 10 to the power of 6. So I'll just press my calculator. So I'm getting 7.12 times 10 to the power of minus 4 farads. If I want this to be in microfarads, I'll divide the answer by exponent -6, which is the same as 712 microfarads. So that will be the capacitance of the earth. That will be the capacitance of the earth. Okay, then that's lesson 1 end there.
At 29 and I find myself wondering what did happen to the last 10. I ran away with my life, fast forward, never turn back again. It's kind of funny that the more we pass time, the more we need to set the rewind. And 19 has to give